Integration by parts. Integration by parts is based on the product rule. Recall that the derivative with respect to x of u of x times v of x is equal to u times v prime plus v times u prime. Now let's rearrange this and write it as u times v prime equals the derivative of the product minus u prime times v. Now let's antidifferentiate both sides. On the left we have the indefinite integral of u of x times v prime of x dx, and an antiderivative of the derivative of the product is the product itself, and then we have minus the integral of v times u prime. Now this is potentially a very useful formula because the integral on the right side is possibly simpler than the integral on the left. Now we usually write this in an abbreviated form where we think of v prime of x dx as dv and u prime of x dx as du. So the formula becomes the integral of u dv equals uv minus the integral of v du. Example. Let's find the indefinite integral of x times cosine x dx. To do this, we'll let u be x and let dv be cosine x dx. Now we need to compute du and v. Du here is simply dx, and v is any antiderivative of cosine x. So we can take v equal to sine x. So the integration by parts formula tells us to write down u times v, which is x times sine x, minus the integral of v times du, which is the integral of sine x dx. So we've exchanged a difficult integral for an easy one. We end up with x times sine x plus cosine x plus c. Another example. The integral of x times e to the minus x over 2 dx. Here again we'll let u be x and let dv be e to the minus x over 2 dx. That makes du equal dx, and integrating e to the minus x over 2 gives us v equals minus 2 e to the minus x over 2. So we have uv equal to x times minus 2 e to the minus x over 2 minus the integral of v du, which is minus the integral of minus 2 e to the minus x over 2 dx. The first term becomes minus 2x e to the minus x over 2. Then we have minus 2 or plus 2 times the integral of e to the minus x over 2. The integral of e to the minus x over 2 once again is minus 2 e to the minus x over 2. So we get minus 2x e to the minus x over 2 minus 4 e to the minus x over 2 plus c. And finally we factor a minus 2 times e to the minus x over 2, revealing the other factor to be x plus 2. Now let's think for a minute about how we go about choosing which factor of the integrand is to be u and which factor is to be included along with dx in dv. Notice that we differentiate u to get du. So we'd like for u to be a factor that gets simpler when we take its derivative. Now notice that dv needs to be something that we can integrate to get v. Generally speaking, we'd like for dv to be as much of the integrand as we can integrate easily. Another example. Let's find the indefinite integral of e to the minus x times sine of 3x dx. Here we're going to let u equal e to the minus x and dv equal sine 3x dx. So we calculate du, it equals minus e to the minus x dx, and we integrate sine of 3x dx to get v equals minus 1/3 cosine of 3x. So our integral becomes u times v, e to the minus x, times minus 1/3 cosine 3x, minus the integral of v du, which is minus the integral of minus 1/3 cosine of 3x, times minus e to the minus x dx. Now let's simplify that second term, writing it as minus 1/3 times the integral of e to the minus x cosine 3x dx. Notice that this step has merely exchanged the integral of e to the minus x sine 3x dx with the integral of e to the minus x cosine 3x dx. Now let's apply integration by parts to that integral. Here we'll let u equal e to the minus x again, and dv is cosine 3x dx. So we calculate du, just as before, it's minus e to the minus x dx, and now we integrate cosine of 3x to get v equals 1/3 sine 3x. Now we need to be careful about grouping here. We have minus 1/3 e to the minus x cosine 3x minus 1/3 of u times v minus the integral of v du, which is 1/3 sine 3x times minus e to the minus x dx. We now have that the indefinite integral of e to the minus x sine 3x dx is equal to minus 1/3 e to the minus x cosine 3x minus 1/9 e to the minus x sine 3x minus 1/9 the integral of e to the minus x sine 3x dx. Now notice that the integral on the right side is just a multiple of the integral that we're trying to find. Now let's add 1/9 of that integral to both sides, and we get 10/9 times the integral on the left, and a little factoring of the other two terms gives us minus 1/9 e to the minus x times 3 cosine 3x plus sine 3x, and we need to add our plus c to the right-hand side at this point. So now we've computed 10/9 of the integral we're looking for. So let's multiply through by 9/10, and we have that our integral is minus 1/10 e to the minus x times 3 times cosine 3x plus sine 3x plus c. So notice that two applications of integration by parts produced a multiple of the integral we were trying to find on the right-hand side. Since the coefficient there was not 1, we were able to simply solve for the integral algebraically at that point. Example. Let's find the indefinite integral of the natural log of x dx. It may be a little surprising that this can be done by integration by parts, since the integrand consists of just one factor. But it turns out we can do this by thinking of natural log of x as u and dx as dv. That gives us du equals 1 over x dx, and dv simply equals x. So the integral becomes u times v, or natural log of x times x, minus the integral of v times du, or the integral of x times 1 over x dx. So we have x times natural log of x minus the integral of dx. So we get x times natural log of x minus x plus c. Notice the advantage of taking u to be the natural log of x. When we take the derivative of natural log of x, we end up with 1 over x, and that takes the natural log out of the problem. Another similar example, the integral of the inverse cosine of x dx. Here we'll let u equal inverse cosine of x and dv equal dx. Now recall that the derivative of the inverse cosine of x is minus 1 over the square root of 1 minus x squared, so du is that times dx, and integrating dx gives us v equals x. So now we have u times v, or inverse cosine of x times x, minus the integral of v times du, which is minus the integral of x times minus 1 over the square root of 1 minus x squared dx. So now we have x times inverse cosine of x plus the indefinite integral of x dx divided by the square root of 1 minus x squared. This integral can be done by a simple u substitution. We let u equal 1 minus x squared, which makes du equal minus 2x dx, and so that integral becomes minus 1/2 of du over the square root of u. Now 1 over the square root of u is u to the minus 1/2 power, and so we integrate that to get u to the plus 1/2 power times 2, so we now have x times inverse cosine of x minus the square root of u plus c, and of course the square root of u is the square root of 1 minus x squared here. Using parts on definite integrals. Suppose we have a definite integral from x equals a to x equals b of u of x times v prime of x dx. Or in other words, the integral from x equals a to x equals b of u times dv. By integration by parts, the indefinite integral will begin with u times v, so we'll end up evaluating u of x times v of x between a and b, and then we subtract the integral of v du. Now this was a definite integral from x equals a to x equals b of v of x times u prime of x dx. This is a very straightforward adaptation of the integration by parts formula to definite integrals. Now let's look at an example. Suppose we want to evaluate the integral from 0 to 2 of x cubed times the square root of 4 minus x squared dx. We're going to let u equal x squared here, and we let dv equal x times the square root of 4 minus x squared dx. Note that keeping a factor of x along with that square root will allow us to integrate that by a simple substitution. So we compute du, that's 2x dx, and we want to integrate dv. Now the x factor there is minus 1/2 times the derivative of what's underneath the square root. So it's clear that v is going to be some multiple of 4 minus x squared to the 3/2 power. Now if we take the derivative of that, we'll have 3/2 times 4 minus x squared to the 1/2 times minus 2x. That minus 2 times the 3/2 is a minus 3. So as it is, we have an extra factor of minus 3, so let's multiply by minus 1/3. That will make the derivative exactly x times the square root of 4 minus x squared. So we have u times v, or x squared times minus 1/3 of 4 minus x squared to the 3/2, all evaluated from 0 to 2, minus the integral from 0 to 2 of v du, or minus 1/3 of 4 minus x squared to the 3/2, times 2x dx. Now let's go ahead and evaluate the first term. Notice that at x equal to 2, v is equal to 0, and at x equals 0, u is equal to 0, so we get 0 minus 0 from that evaluation. Now let's write the second term as minus 1/3 of the integral from 0 to 2 of 4 minus x squared to the 3/2 times minus 2x dx. We're keeping the minus 2x dx together because minus 2x is the derivative of 4 minus x squared. So now we'll do a substitution here. We'll let u equal 4 minus x squared, which makes du equal minus 2x dx, and we'll transform our limits of integration as well. When x is equal to 0, u is equal to 4, and when x is equal to 2, u is equal to 0. So notice we have this backwards integral with a negative sign in front. So let's go ahead and absorb the minus sign by switching the limits of integration around. Now we antidifferentiate u to the 3/2, which gives us u to the 5/2 times 2/5. So we have 2/15 of u to the 5/2 evaluated from 0 to 4. So we end up with just the value of that at 4, which is 2/15 times the square root of 4, or 2 raised to the 5th power. That's 2/15 times 32, or 64/15. Reduction formulas. Let's suppose that capital F prime of x is equal to little f of x. That is, capital F of x is an antiderivative of little f of x. Then, if we perform integration by parts on the indefinite integral of x to the nth power times f of x dx, what happens? We'll set u equal x to the n, and we'll set dv equal to f of x dx. Then the differential du equals n times x to the n minus 1 times dx, and v is simply capital F of x. And the indefinite integral becomes u times v, or x to the n times capital F of x, minus n times the indefinite integral of x to the n minus 1 times capital F of x dx. We refer to this as a reduction formula because the step of integration by parts, as shown here, reduces the power of x by 1. So if n is a positive integer, we have the potential of being able to use this formula repeatedly until the power of x is 0. With little f of x equal to e to the ax, and capital F of x equals 1 over a times e to the ax, this formula becomes the indefinite integral of x to the n times e to the ax dx equals 1 over a times x to the n e to the ax minus n over a times the indefinite integral of x to the n minus 1 times e to the ax dx. Now notice that the same formula could be applied to the integral on the right-hand side. For example, suppose we want to find the indefinite integral of x cubed times e to the 2x dx. So here a is 2 and n is 3, so an application of that formula gives us 1 over 2 times x cubed e to the 2x minus 3/2 times the integral of x squared times e to the 2x dx. So now we'll apply the same formula again to the integral on the right-hand side, this time with n equals 2. So we have 1/2 of x squared e to the ax minus 2 over 2 times the integral of x to the first power times e to the 2x dx. Now we apply the formula again. The integral of x times e to the 2x is 1/2 of x times e to the 2x minus 1 over 2 times the integral of x to the 0 power times e to the 2x dx. Now finally we evaluate this integral. Minus 1/2 of the integral of e to the 2x dx is minus 1/2 e to the 2x divided by 2, or minus 1/4 e to the 2x plus c. Now let's remove all these parentheses and factor out 1/8. The result is 1/8 e to the 2x times the cubic polynomial 4x cubed minus 6x squared plus 6x minus 3 plus c. Now let's apply the same general formula to the situation where little f of x is equal to cosine of kx. An antiderivative of cosine kx is 1 over k times sine kx, so we'll use that as capital F of x and write x to the nth power times 1 over k times sine kx minus n over k times the integral of x to the n minus 1 sine kx dx. Similarly, if we start with little f of x equals sine kx, we can use capital F of x equal to minus 1 over k times cosine kx. So we have minus 1 over kx to the n cosine kx plus n over k times the integral of x to the n minus 1 cosine kx dx. So notice that if we start with x to the n cosine kx, an application of the first formula gives us an integral involving sine kx, to which we can apply the other formula, again getting an integral involving cosine kx, to which we can apply the first formula again, and so on. Now let's look at a different kind of reduction formula here. Reduction of powers of sine and cosine. Turns out that the indefinite integral of the nth power of cosine x dx equals 1 over n times the n minus first power of cosine x times sine x plus n minus 1 over n times the integral of the n minus 2 power of cosine x dx. So notice that the power on cosine is reduced by 2 each time this formula is applied. The corresponding formula for the nth power of sine x dx is minus 1 over n times the n plus first power of sine x times cosine x plus n minus 1 over n times the integral of the n minus 2 power of sine x dx. Each of these formulas is derived in a similar way. Let's go ahead and look at the derivation of the formula for the nth power of cosine x. We do this by integration by parts. Let's let u equal the n minus 1 power of cosine x, leaving dv to be cosine x dx. Then du is equal to minus n minus 1 times the n minus 2 power of cosine x times sine x dx by the chain rule. Now we integrate dv to get v equal to sine x. So integration by parts says that that integral is equal to u times v, or the n minus first power of cosine x times sine x, minus n minus 1 times the integral of the n minus 2 power of cosine x times the square of sine x dx. Now let's replace sine squared x with 1 minus cosine squared x. Next, let's multiply out that integrand and break that whole thing up into two integrals. Notice that we now have a multiple of the integral that we're trying to compute on the right-hand side, which basically gives us an equation we can solve for the integral. We'll add n minus 1 times the integral to both sides, and we have n times the integral equal to the n minus first power of cosine x times sine x plus n minus 1 times the integral of the n minus 2 power of cosine x dx. Now dividing by n gives us our reduction formula. Now let's use this formula to work an example. Say we want to find the indefinite integral of the fourth power of cosine x dx. So we apply the formula with n equals 4, obtaining 1/4 cosine cubed x times sine x plus 3 over 4 times the integral of cosine squared x dx. Next, we apply the formula to the integral of cosine squared x. That gives us 1/2 of the first power of cosine x times sine x, plus 1/2 of the integral of the 0th power of cosine x dx, or just the integral of dx. Now that integral simply gives us x plus c, and by factoring 1/2 from the two terms in the parentheses, we end up with 1/4 of cosine cubed x times sine x plus 3/8 of cosine x sine x plus c. Now let's go ahead and factor a 1/8 out of the whole thing, and we have 1/8 of 2 cosine cubed sine x plus 3 cosine x sine x plus 3x plus c.